Hey everyone, welcome back. So today's video we're going to continue the concept of D block elements and we're going to talk about the complex formation and their stereoisomers showed by the transition elements. Let's look at these two complex structures. On the left hand side you have a complex of iron and on the right hand side you have a complex of copper. If you write the molecular formula, the iron complex would be Fe hexacyanoferrate. And then on the right hand side you can see it's going to be tetrachlorocopper complex. In the case of the complex on the left hand side, the coordination number is 6 because there are 6 ligands each making one bond with my iron transition element, while on the right hand side the coordination number is 4 because there are 4 bonds. If you try to find the oxidation state of the metal ion, you can see that each cyanide ligand has a charge of -1, so it's a total of -6. Let's say iron was having X oxidation state, but the total charge of the complex is -3. So to solve X, we can find the oxidation state of iron ion to be +3. We can repeat a very similar mechanism on the right hand side to find the oxidation state of the copper ion. There are 4 chloride ligands each with a -1, while copper is equal to X. The total charge on the complex is -2 and copper turns out to be +2 ion. The complex on the left hand side is the octahedral complex, while on the right hand side you can see a tetrahedral complex. Now I'm going to show you how to write or how to draw these structures with complicated ligands, for example ethylene diamine. Ethylene diamine, which is a bidentate ligand, makes a complex with iron, and I'm going to show you all 3 possible ways to draw the structure with iron and 3 ligands of ethylene diamine. You know the structure of ethylene diamine includes 2 imine group, one on the left hand side, one on the right hand side, and the center part is basically 2 carbon atoms. So it is the nitrogen atom you can see on the left hand side which is making the structure, and you can see how I am drawing this structure with 2 nitrogen atoms making the coordinate bond, while the CH2CH2 chain is in the middle. Another way of drawing this structure is the skeletal formula, where you write the atom nitrogen and then the remaining 2 carbon chain is represented skeletally, which means through simple lines. The last possible way is making an arc and just writing small en in the middle of the arc. The arc represents bidentate ligand. So all 3 ways are possible to draw the structure of ethylene diamine, and you can see I'm putting the charge on the complex also. In this case, the coordination number of iron ion is 6 because each ethylene diamine makes 2 coordinate bonds because it's a bidentate ligand. So 3 ethylene diamine will be making 6 coordinate bonds, 2 by each ligand. Now I'm going to show you how to draw the structure with the oxalate ligand, or you can also call it the ethane dioate ligand. Oxalate has basically 2 carbon atoms and both have the carboxylic acid group. It is the acid oxygen atom which has the lone pair on it, and that makes the coordinate bonds. In all 3 structures, basically iron is my central transition metal ion, and oxygen is the atom which makes the lone pair and coordinate bond. On the left hand side you can see I am drawing the displayed structure showing all the carbon atoms and the oxygen atoms. In the middle I am going to show you the skeletal formula, where I just draw the oxygen atoms and I draw simple lines to show the carboxylic acid group, like this. On the right hand side you can use the arc way, where I can just make an arc and I can put OX in the middle. This is another way to show bidentate ligands. When you put square brackets, you will realize that the net charge on the complex is going to be -3 because each oxygen atom in the middle has a -1 charge, so that's a -6, and iron is +3, so the net charge on the transition metal complex is going to be -3. Now I'm going to show you how to make the complex using the ligand EDTA. EDTA has a charge of -4. And if you have iron, let's suppose in whatever oxidation state like +2, it will give you a net charge on the complex. Now, EDTA is very complicated ligand structure. It has an ethylene group in the middle, then there is one nitrogen on either side, and there is two carboxylic acid groups on each nitrogen atom. It is the nitrogen atoms and the oxygen atoms which make the coordinate bond. If you have EDTA, it is itself a hexadentate ligand. The first two coordinate bonds are made by the nitrogen atoms showed in red pen over here. Then you can see I am drawing the carbon chain, which is the 2-carbon chain, and now I am going to draw the oxygen atoms with a purple pen. The remaining two bonds are made by the oxygen atoms from the carboxylic acid group like this. Your examiner will never ask you to draw it, but I want to show you how a hexadentate ligand works. The remaining two oxygen atoms represented here in the green pen are from the other nitrogen atom carboxylic acid groups. You can see how a hexadentate ligand covers the entire iron atom or iron ion to make the complex. Now let's talk about stereoisomerism as present in the transition metal complex. We'll start with the geometric category, which includes cis-trans isomers. The cis ones are the ones which have net dipole on them, and the trans ones do not have a net dipole. They do not have any net dipole. For example, to understand this, we have this example of tetra-echo dichloroferrate complex. We have 4 water ligands and 2 chloroligands. In both cases, I am putting iron as the transition metal ion in the middle. Now, for net dipole to happen, I am putting both negatively charged chlorides on one side and the neutral water ligands on the remaining sides of the complex. You know, chloride has a charge of -1 on them, so there's a net dipole towards the side, towards the end, where there are 2 chloroligands. In order to have no net dipole, I am putting both chlorides on the opposite ends while I am putting the water ligands on the remaining 4 bonds. If both chlorides which have the negative charge on the opposite ends, they will cancel out the net dipole. The net dipole will be cancelled, will be 0, because the dipole from both chloro will cancel each other. So on the left hand side, you can see the cis isomer which has net dipole. It is the cis complex. While on the right hand side, you have no net dipole, and that is the trans ones, where both similarly charged ligands cancel out each other. So you have the same ligands on the opposite ends in the trans one. Let's talk about optical isomers, which include mirror images of isomers. So I have a mirror on the right hand side and I have the complexes on the left hand side. On the left hand side, you can see I have my cis isomer that we had just talked about, and at the bottom I have my trans isomer from our previous conversation. In order to make the mirror image of the cis isomer, this time I'll put both chloride ligands on the left hand side instead of the right side, and I'll put the remaining water ligands exactly in the form of mirror image. And this looks like how mirror images are formed. When I try to draw cis isomer in the mirror image, you can see it's a non-superimposable mirror image made by the cis isomer. But for the trans ones can't make mirror images, so they can't make optical isomers. Always remember that trans ones can't make mirror image optical isomers. Let's have another example where I am keeping 3 ethylene diamine ligands with the iron to make a complex. You know, in order to have 3 ethylene diamine ligands, I can use the structural or skeletal formula where I am keeping the nitrogen atoms represented while the remaining part of the chain is very simple as lines. This entire complex has a charge of +2, but that's not our concern over here. In order to form the mirror image, I will make sure that this time I will draw the structures in exactly opposite manner. So instead of drawing the structures on the right side, I am drawing them on the left side. Instead of making bonds on right, these bonds are on the left side. Exact mirror image is made, while the charge of the complex is obviously +2, it's not going to change. So you can see that I can use the arc method or I can use the skeletal formula method to show how mirror images are made for these kind of complexes. I hope this idea is clear because next we are going to do some past paper practice. Stay tuned, guys.